So this is the big result we want to prove in this lecture. So if A is normal integral domain, so that is A is its own integral closure in its field of fractions, then that would imply that this AT is also normal integral domain. So let K be the field of fractions associated with this integral domain A. And then this KT, this is a field of fractions for this polynomial ring AT. So this is rational functions of AT. So this KT looks like this: f over g, where f is a polynomial in this AT and g is a polynomial in this AT. So you pick up a p in this field of fractions of AT, and this is integral over AT. So you pick something which is integral over AT, and we have to show that this AT is normal integral domain, that it is integrally closed. So if you pick some polynomial in its field of fractions which is integral over AT, we want to show that p itself lies within this AT. So first note that p itself is integral over this KT, because K is a field. So if K is a field, you attach this to it, this becomes a unique factorization domain. So P lies within this KT. So this would imply that P lies within KT, because KT is a unique factorization domain, so it is normal, that it is integrally closed. So to show P lies within AT, we have to show that the coefficients are integral over A. So this P lies within KT. So we have already seen here that only the coefficients could be rational. We do not have something like this, we have something like this. So there's square brackets here rather than round brackets here. So it is a polynomial, not a fraction like this, but its coefficients might lie in K. So they might lie in K. So we want to say that the coefficients actually lie are integral over A. So because if they are integral over A, then we are already assuming A is a normal integral domain. So that means its integral closure is same as A itself. So if they're integral over A, the normality of A would imply that they lie in A. So this is what we want to show. So everything will follow if we can show that the if P lies in AT, we need to show that coefficients are integral over A. So this will follow from this proposition which we will now prove. So say A is subring of B. Instead of B, you can write now K. Say B is K, field of fractions. So if a polynomial in BT is integral over AT, or you can say a polynomial in KT is integral over AT, then each of its coefficients is integral over A. And this solves our problem right here. So because see that this P in KT is integral over AT and P lies in KT. So P lies in KT. So say polynomial P lies in this KT, and this polynomial is integral over AT. So this polynomial is integral over AT, then each of its coefficients is integral over A. So coefficients are integral over A, and that ends the proof of this proposition. So only thing we now need to prove is this proposition. So now we prove this proposition. So say A is a subring of another ring B, and say we have a polynomial P in this polynomial ring BT, and this polynomial is integral over this polynomial ring over A. So then each of the coefficients of P is integral over A. So we start with some polynomial P, and this is integral over AT, so it is root of some polynomial like this, where each of the coefficients lie within this ring AT. So the coefficients themselves are polynomial over ring AT, and this P is root of this polynomial. So you fix some number R, and this number R will become useful later on as maximum of degree of P, this degree of our polynomial P, and each of these polynomials f0, f1 all the way to fn minus 1. So R is greater than this, and then you set P1t as P of t minus t of R, and you have another polynomial, say q1 of x, which is q of x plus t to the R. So this we are writing because now P1t is a root of q1 of x, because if you plug P1 of t here, then instead of x you're plugging p1, so here you will again plug p1, but p1 is pt minus tr, so p minus tr, this tr will cancel with this tr, you have q of p, but p is root of this, so p1t becomes root of q1. Now this, if you expand, we can again write it in this form, x to the n plus gn minus 1 xn minus 1 all the way to g0, where gi is again in at, because we are just adding tr essentially. We are just adding tr essentially, replacing every x with x plus tr. So these will multiply out with some tr here, and you will again get these gi's in at. Now there is a reason why we are choosing r as the greater than each of the maximum degree, because once you plug p1 here, so now we start plugging p1 here. So if you plug in p1 here, then p1 is the root of this equation, as we said before. So if you plug in p1 here, this becomes 0. This 0 comes right here. And then instead of x, we are writing p1, so p1 to the n, gn minus 1, p1 to the n minus 1 all the way to g0. Again, each gi lies within at. Now you take this g0 here and take p1 as common out. So now we have chosen r so as this g0 and p1 are monic polynomials, and this g0 has coefficients in a. So g0 has coefficients in a, and so therefore these coefficients are also integral over a, because precisely because if you lie within a, then you are integral over a by using the linear equation. So now g0 has coefficients in a, and now this equation implies that p1 divides g0. Now if p1 divides g0, then we have a lemma which will show that coefficients of p1 are also integral over a. So let us consider the lemma which will solve our problem here. So consider monic polynomials f and g in some polynomial ring by such that g divides f with b as an a algebra. So b contains a, you can say. So b, say, contains a. So if coefficients of f are integral over a, then coefficients of g are also integral over a. So in this case, our f is g0 and our g here is p1. So the lemma will show that coefficients of p1 are integral over a, because the lemma shows that coefficients of g are integral over a, and we are setting g as p1 here, and coefficients of g0 are integral over a, or f are integral over a, because g0 has its coefficients lying within a. So let us prove this lemma now. So first notice that if you are given any polynomial f, you can always find its splitting ring, and say its splitting ring is b prime of phi, and essentially you find the splitting ring by just adjoining the roots to the base ring on which you have defined it. So the simple example is, say you start with something like this bx, and you do like this f, so this will give you this b adjoined with some alpha, where alpha is the root of f. So now you can consider your this f in this bigger ring, b alpha of x, and then here at least you can divide with x minus alpha, and then you can continue this process inductively to find a splitting field. So essentially this was in Galois theory how to construct splitting ring for any polynomial f, and heuristically you just say assign all the roots to the base ring, you attach it to all the roots to the base ring, and that will give you the splitting field for f. So say this b prime of y is the splitting field. So the roots of f lie in b prime, they are integral over this ring C. So roots of f, they are integral over such a ring a, c0, c1 all the way to cn minus 1. So why are they integral? Because the roots satisfy a monic polynomial f, because minimal polynomial is always f. So these are monic polynomials are f. We are starting with a monic polynomial f, and the coefficients of the monic polynomial, they lie in this ring a adjoined with c0, c1 all the way to cn minus 1, because this c0, c1, cn minus 1 are precisely the coefficients of f. So roots of f are integral over this. So roots of f are integral over c, which is precisely this. Now by transitivity of elements being integral, we get roots of f are integral over a. So each of the coefficients here, so c is just constructed from a by adjoining some coefficients. So each of these coefficients here, we say the coefficients of f are integral over a. So each of these coefficients are integral over a. So c is integral over a, and roots of f are integral over c. So this relation is integral. Roots of f are integral over c, and c is integral over a. So this would imply that roots of f are integral over a. So this is just the transitivity property of being integral. So roots of f are integral over a. So now coefficients of g. So what are coefficients of g? So g splits in this b prime y because g divides f. So if g divides f, then obviously so the roots of g, if f splits completely, then roots of g are contained within roots of f. So say g becomes something like this: x minus alpha 1 times x minus alpha 2 all the way to say x minus alpha m. So now you expand it out. All the coefficients of g, this will be a monic polynomial, all the coefficients of g would be generated by some product of roots. So you add the roots or take products of them or whatever. So just combinations of roots. So coefficients of g are generated by common roots of g and f. So obviously all these roots are common to f also because g is dividing f and f splits completely. So the coefficients of g are generated by common roots, and therefore these coefficients are integral over a. This precisely because if two elements a and b are integral individually, so here alpha 1 alpha 2 all the way to alpha m, the roots are integral individually, then their combinations are also. So then a plus minus b, a, b, or whatever combinations of them are also integral. And this we have shown before, that elements integral over a ring form a subring. You can add them, multiply them, and you will still be in that subring. So that's the end of the story. So we have been able to show that if the coefficients of f are integral over a, then the coefficients of g, where g divides f, are also integral over a. And that finishes the proof of our first proposition, that if a is a normal integral domain, that is, if a is integrally closed in its field of fractions, then AT is also a normal integral domain. That is, this polynomial ring AT is also integrally closed in its field of fractions, and field of fractions of this is just this KT, if field of fractions of A is K.